All right. So thank you for the introduction. So I'm going to talk to you about reservoir computing in general. So this talk will basically serve as an introduction to the framework of reservoir computing. And the first slide here is a summary of my talk. Rather dramatic, I know, but it summarizes what I'm going to cover. So I'll talk about how performance metrics for nonlinearity and memory can be used to optimize the performance of a system called a reservoir computer, and how it can be used to classify different things. So in this task, we did spoken digit classification, and the substrate for this was a Skyrmion system. So I'll introduce reservoirs in general, but we explore the topic under my particular field, which is Skyrmion dynamics. So before I go on, I'd like to thank my collaborators at the University of Duisburg and Ghent University in the MUMAX group, without whom this work would not have been possible. So to start with, convolutional neural networks. So these are all the rage these days. They're everywhere, from our phones, our TVs, our toasters for some reason. Never ends. And with the onset of large language models like ChatGPT, BARD, and a few others jumping in the race, it only seems to continue. So all this is thanks to the artificial neural network. So in this particular model, you have nodes that are weighted by some number and some lines, some weights connecting them in such a configuration. So the number of nodes you have in your hidden layer depends on the application and the type of specific architecture. So in this, in neural networks, what we do is we train the system to recognize something or to predict something. So in this particular example, this is image recognition. So suppose I have a labeled image of this thing, pass it through the neural network, and get some answer at the end. So this is labeled. I check what the network predicts and compare it to what the actual answer is. And if the answer is not right, go back, tune all these weights, do it all over again until it becomes satisfactory. So quick check, prediction. What do you think this is? Just shout it out. What does this look like?
A dog.
A dog. Oh, wow, overwhelmingly. Panda, nice. Well, the system thinks it's an animal's face, of course. But puppy is a close second, so the dog people win this one. Yeah, I don't know where this came from. But even the system is not so confident with this answer. Yeah, so this is basically how neural networks work. Well, in the static case. So suppose I give, you have data that has temporal dependencies. So that means there's a time element, like time series data. So the problem with doing this is that you have data points at every single point in time. And to alleviate this problem, what we do is we take some part of the output from the previous time step, feed it into the hidden layer at the current time step. And this system is called a recurrent neural network, which is basically the same but with a time component inside. So in the literature, you find that that whole thing is just replaced by something simpler to comprehend, which is input, some hidden layer called the recurrent layer with some nodes that interconnect, and then the output layer as well. Now, modern AI architectures work exceptionally well. This does not need to be stated by me. They work so well, in fact, that some people think they work too well. So if you look at the news cycle lately, you'll be inundated by news such as this. So you have different founders and researchers talking about the dangers of AI and what it poses for our future. Is it the harbinger of the death of our civilization as we know it? So the question is, if it works so well that it's already triggering talks of policy change, is there any room for other computational frameworks? Have we reached peak computing? Should we just continue iterating upon what we have now and stop doing more research? Well, to answer this question, you look at the failing of current neural networks. So to start with, costs. They cost a lot to train these networks. So it's estimated that training the state-of-the-art large language model such as ChatGPT to only 13% would consume, would emit as much carbon as powering a home for 1 year, in the US no less. We also look at the financial costs. So training such a model costs $4 million, and GPT-3 is not the current state of the art. You have GPT-4, and then you have a few others that are trying to take the crown. And undoubtedly, they cost way more than this amount. Not just that, you also have time costs. So using several GPUs, which is the computational unit for running these things, it takes months just to train. Is it clear? It takes several months just to train a system to run inference. So with this, there's room for improvement. And in comes a certain scheme of computing called reservoir computing. So the way reservoir computing works is we use the recurrent system. So just as I showed you before, input layer, recurrent connections, and some output layer. But the trick here is that we fix the weights in the input and the reservoir layer. We just randomly have them, and then we fix them. And in such a way, we only train the outputs using simple techniques such as linear regression. And as you'd imagine, this greatly reduces training costs. Now, how does reservoir computing work exactly? Why? It seems absurd that if you have a random fixture of weights, you should get performance that's close to what would happen if you optimize the weights. Well, to study this, let's look at an example of time-dependent shapes with different colors. So you pass this input into a reservoir. And what this reservoir will do is it projects it into some higher dimensional latent space. So in this case, similar features are grouped together in such a way that you can use hyperplanes to separate data. Now, looking at this is just a matter of perspective of where you look at this higher dimensional projection. In the case of this 2D data, it's 3-dimensional, but it can be n-dimensional. It's a matter of perspective. So if you look at it from a different angle, instead of grouping them by color, you can group them by shape in such a way, or other properties that you'd like to measure. So your output becomes grouped by color, by shape, and you can also make a prediction of what the next phase of the series should be. Now, what does it take to make a good reservoir computer? Well, it should be capable of the nonlinear transformation. So projecting your data into a higher dimensional space, and then you separate using hyperplanes. It should have a fading memory because we want to apply this to time-dependent data. So that means it should be able to recall past inputs up to a certain point in time. And of course, it should have a unique response to the input because you want your results to be reproducible. You want computing to be done effectively. So what can be a reservoir computer? What constitutes to be used as a reservoir computer? So you can have different types. And in the literature, we have a lot of different types of physical reservoir computers. So we have electronic memristor systems, for example, photonic systems, mechanical systems like this octopus. Don't ask me why this shape was chosen, but it works. Biological systems like a culture of cells with electrodes on it. And my personal favorite, a bucket of water. Oh, it's not working. And you can have many others as well. Sorry, just give me a moment.
Sounds cool, advances in artificial life.
Oh, yeah. Water is an advancement in artificial life, it turns out. So yes, so you can have several different types of candidate systems for reservoir computers. It's not just limited to this. Oh, I thought that would do it. OK, I'll just stand here, I guess. So what can you do with a reservoir computer? Well, there's several things you can do. You can do prediction of chaotic systems and time series predictions, so such as weather forecasting. We could have used that here. Anomaly detection, classification, which is what I'm going to talk about in the later part of my talk, And you can also use it to control robots and edge computing and a lot of other applications. So again, this is the summary of what reservoir computing is. If you take one thing from my talk, at least it's the general layout of what a reservoir computer is. Input into a reservoir layer that projects into a higher dimensional latent space, such that you can perform training on only the output using simple techniques like linear regression. Now, my system, the system I use to investigate reservoir computing is a Skyrmion fabric system. So this is a system with Skyrmions just randomly scattered about, and we call this our reservoir. If you don't believe me, those dots are Skyrmions. Now, the reason we use Skyrmion systems is because they have really ultra-low power, as all of you would know. And also, the noise in the system just adds to the reservoir dynamics, which adds to nonlinearity and improves performance, actually. So these systems have already been experimentally realized by the Chloe group at the University of Mainz, and also for handwritten recognition by the Otani group at the University of Tokyo. Now, if we look at our criteria, Skyrmion fits this nicely because it's inherently nonlinear. It has the fading memory from the dynamics and the underlying structure of the microstructure on which the Skyrmions are overlaid. And then you also have an interpinning of spin torques, local pinning stability to ensure that you have the unique response, or as it's called in the literature, the echo state property. Now, when you have a system like this, you can study certain performance metrics to quantify how well your reservoir performs. So if from my talk you can gather that nonlinearity and memory are key considerations to have in a reservoir computer. So to study how to improve reservoir performance, we start with acknowledging that randomization leads to efficiency, but at the same time, the quality of randomization has an effect on how your reservoir performs. So how can we improve this randomization? Well, the best way to do this is to tune hyperparameters to enhance performance. So hyperparameters are basically parameters that cannot be learned from the input data, from the training data. So your system cannot learn these parameters. You need to tune them on your own from the outside. So in the case of a magnetic system, it would be anisotropy, DMI, and what have you. So we study these and how they influence reservoir quantities, the qualities of a reservoir, sorry. So the main focus of my talk and the first part of my study is looking at spatial metrics. So this is using, this is when your reservoir relies on a spatially resolved readout. So take this reservoir here, which is, again, Skyrmions, as I said, randomly distributed. And in this case, given an input, they react to this input in such a way. Now, you can define local metrics to quantify the performance of this. How can one do this? Well, you can create estimators. So these are basically quantities that estimate the degree of nonlinearity and the degree of memory capacity within your system. So I'm not going to go into details on how exactly you do this, but in the case of nonlinearity, it's worth noting that you estimate the degree of linearity in the system, and then you can infer what the nonlinearity should be in the system. And with these estimators, using labeled data, you can compare what these things estimate to the true values, and then tune your weights and your biases, and you have a measure for nonlinearity and memory capacity within the system. So I won't go into the details, but basically it should take a form like this. Now, you measure, a way to quantify the performance of these estimators is using the R2 correlation coefficient. So basically, R2 of your estimator and your training data should be 1 if it's a perfect prediction, and 0 if there's no correlation between the two quantities.
Can it be somewhere in between?
Sorry?
Can it be somewhere in between?
Yes, it can be somewhere in between. Yes, it can very much be somewhere in between. So perfect prediction, no correlation, and then, yeah, somewhere in between. Yes. So with this, we have a measure of nonlinearity and a measure of memory capacity within a reservoir computer. And if you apply this to a magnetic system, you get such graphs. So in this case, we have nonlinearity and memory, and from this, one can see the memory nonlinearity trade-off. So this is...
What number 5 of number 1 means?
Yes, that's a very good question. So if you notice, memory capacity is a summation because it looks at different time steps in the past. So if you go a few time steps down, then your quantity increases. Whereas with nonlinearity, it's just a value between 0 and 1. How 0 means linear, 1 means nonlinear. Yes, so you see the memory nonlinearity trade-off, which means that if you have high memory, more likely you have very low nonlinearity, and vice versa. And the reason for this is somewhat intuitive, but also a bit specific. You can ask me later, and we can have a conversation. Well, these metrics can be computed in parallel using tiny data sets, and they can help boost parameter searches to optimize a reservoir. And that's exactly what we did. So the last part of my talk is classification performance. So in this case, I chose spoken digit classification because it's a more complex task, and it's very time sensitive and a good way to measure the way the reservoir works. So I'll start by introducing the reservoir first. So I talked about it, Skyrmion distributed, and then you have 39 contacts on each side. The reason for that will become clear later. But the advantage of this is that you have more mixing of signals because you have several signals coming in, and then the reservoir likes nonlinearity. You have even power distribution, and you also overcome the noise floor. So Lisa talked about how you have thermal fluctuations in the system. You don't want too much of that because perfect thermal contributions carry no information, and you want to avoid that. Okay, so I'll just quickly run you through what exactly I did. So I start with an audio waveform. And from this audio waveform, we create a spectrogram. So that's isolating the frequencies at a given with time. And the color represents the frequency range. So at a given sliver of time, we can create voltage signals from these color intensities. So we create positive voltage and the same voltage but negative. We feed this into the reservoir system. So the left-hand side has the positive voltage and the right-hand side has the negative voltage. The reason this is done is to create a high dynamic range because in sounds you have really, really small signals. And if you ground this, then those signals might be lost. So if you create this gradient, you have a chance of capturing those effects as well. And you carry out a spatially resolved readout. So in this case, you look at the change of magnetization over time. And you you split it into cells like this. And if you're wondering, that waveform is the number 4. Okay, so with this, we create a model from the output that the reservoir learned from. And we find 97% model accuracy. So once you have a model, you have to test it. So we test it with data that it wasn't trained on to see how well it can generalize. And to visualize this, I'll use a performance matrix. So basically, it means that perfect prediction falls on the diagonal. If class 0 is class 0, it's correct, and vice versa. And everything that's off diagonal is not correct. And even with this, with the data, it performs exceptionally well. And just as a sanity check, we bypass the reservoir. We see what would happen if we just fed the input data and just did the training on the output without even going through the reservoir transformation. And we, of course, don't see very good performance. Now, we do the same for the female data sets, as is common in the literature. And this gives even higher prediction. which is very nice. So it seems generally women are easier to understand. Data is in. Do with that information as you please. This is the highest ever immaterial performance of a reservoir computer for spoken digits. And it's a very exciting testament of what Skyrmion systems or magnetic systems are capable of. So to conclude, I'd just like to summarize the key takeaways from this talk. Reservoir computing is a general and efficient framework that can be used for several things. You can use local metrics to quantify and tune a reservoir to perform very well and excel at certain tasks. And this is exemplified in this case using classification, spoken digits specifically. And thank you very much for your attention.